Everyone, and welcome to this high-yield explainer. If you are gearing up to review the absolute foundational concepts of biochemistry, well, you've landed in exactly the right spot. Today, we're unpacking the ultimate exam review guide, and we are going to look at the very blueprint of life. We'll build our understanding from the ground up, starting with simple protons and moving all the way up to incredibly complex protein machines. Let's get right into it.
Okay, let's just dive right into this outline. We'll be hitting 5 key sections today: acids, bases, and pH, then amino acid building blocks, protein structure and folding, and Finson's landmark experiment, and finally, allosteric protein models.
Kicking things off with Section 1, acids, bases, and pH.
So, starting with the Bronsted-Lowry concept, in biochemistry, the rule is pretty simple. An acid is a substance that donates a proton, and a base accepts one. But, don't just picture these as static little molecules floating around aimlessly. Actually, it's way cooler than that. Think of it like a lightning-fast, bucket brigade-style transfer of protons shooting across biological water networks. It is incredibly dynamic.
Now, here is an absolutely massive concept for your exams: the difference between strong and weak acids. Strong acids, think hydrochloric acid, are totally all in. They dissociate 100% in water. Weak acids, on the other hand, which, by the way, make up our standard amino acid functional groups, they only partially dissociate. They set up this reversible, dynamic equilibrium. And this exact balance, that's where the famous Henderson-Hasselbalch equation comes in. It mathematically links the environmental pH to the intrinsic strength of that weak acid, so you know exactly how it's going to behave in a solution. And why does all this mathematical balancing act actually matter in the real world? Well, because human blood is tightly buffered at a highly volatile pH of exactly 7.40. No wiggle room there. Our bodies use a carbonic acid bicarbonate buffer system that's precisely tuned to this tiny range just to prevent lethal swings in blood acidity. Literally, without these weak acid equilibriums, we wouldn't survive a simple trip to the gym.
Moving right along to Section 2, amino acid building blocks. Now, what's really interesting here is how amino acids are amphoteric. Because they have both an acidic carboxyl group and a basic amino group, they can act as both acids and bases. Crazy, right? At that physiological pH of 7.4 we just talked about, they fully ionize into what we call a zwitterion. It's this really fascinating dual-charged yet totally net neutral hybrid molecule.
Okay, pay close attention here, because these 3 amino acids are classic exam traps. They are the rule breakers. First up, glycine. Since its side chain is just a single tiny hydrogen atom, it's the only standard amino acid that is completely achiral, and it's super flexible. Next is proline. Actually, scratch that, it's technically an amino acid, featuring this rigid pyrrolidine ring that literally locks its backbone into place. It's a famous helix breaker. And finally, cysteine. While every other standard L-amino acid rocks an S configuration, cysteine bucks the trend. Thanks to its heavy sulfur atom, it has an absolute R configuration. Plus, it's the only one that can form those strong, covalent disulfide bridges.
Let's step up the ladder to Section 3, protein structure and folding.
Let's see how this all builds, because the structural hierarchy of proteins is perfectly sequential. It's like a giant puzzle. We start at the primary level. That's just your linear sequence of amino acids, locked together by really rigid peptide bonds. Then the backbone folds locally into secondary structures, your alpha helices and beta sheets, which are stabilized by hydrogen bonds. Step 3, the tertiary level, is the complete 3D folding of that single chain. This is driven largely by the hydrophobic effect, just shoving all the nonpolar side chains into the center to hide from water. And finally, the quaternary level. This is where multiple independent protein subunits come together to form these massive, functioning oligomeric assemblies.
But hold on, proteins can't just fold any way they want, willy-nilly. Steric hindrance is the boss here. The peptide bond itself is rigid. It's got that partial double bond character. So the only flexibility the backbone actually has is at the single bonds flanking the central alpha carbon. We define these by the phi and psi torsion angles. The Ramachandran plot is basically this genius stereochemical map. It visualizes exactly which combinations of these angles are allowed so that atoms won't literally crash into each other. No atomic car crashes allowed.
And those allowed angles we just mapped, they correspond perfectly to our 2 main secondary structures. On one side, we've got the right-handed alpha helix. It's a tight, coiled structure with exactly 3.6 residues per turn, stabilized by repeating vertical hydrogen bonds. And on the flip side, we have beta-pleated sheets. These are formed by extended, zigzagging strands where the variable side chains point strictly up and down. Why? Just to avoid crowding each other out.
All right, shifting gears to Section 4 and Finson's landmark experiment.
To really grasp in Finson's genius here, I want to pose a highly testable scenario directly to you. What happens to a denatured protein if we remove the reducing agent before removing the triotopic urea? Think about it. And Finson deliberately used 8 molar urea to completely disrupt non-covalent forces, and beta-mercaptoethanol to snip apart covalent disulfide bonds. But, and this is a huge but, it was the order in which he removed them that literally changed biology forever.
There are 2 experimental pathways here that are absolutely crucial for your exams. The first is our control, true native renaturation. When Anne Finson dialyzed away the urea and beta-mercaptoethanol simultaneously, the non-covalent forces correctly aligned the backbone first, and then the native disulfide bonds locked into place perfectly. But look at this second pathway. Scrambled misconformation. If you remove the beta-mercaptoethanol first, while the protein is still trapped in urea, while the hydrophobic effect is still completely suppressed, the protein just can't fold. So when oxygen is introduced, it forces these random, totally inactive cysteine pairings, leaving us with a scrambled, useless mess.
So the absolutely crucial point here is how he rescued it. Anne Finson added just a tiny, trace amount of beta-mercaptoethanol back to that scrambled mess, but this time in the absence of urea. It acted like a molecular eraser, selectively cutting those wrong, scrambled bonds. Because the urea was finally gone, the thermodynamic driving force naturally took over, folded the protein perfectly, and returned it to 100% catalytic activity. No way, right? It definitively proved that the 3D shape of a protein is encoded entirely within its primary amino acid sequence.
And that brings us to our final stop, Section 5, allosteric protein models.
So when multiple subunits work together, we often see positive cooperativity, meaning one ligand binding makes it way easier for the next one to bind. But how does the protein actually move? Well, the concerted, or MWC model, operates on incredibly rigid rules. It relies on a strict symmetry rule. All subunits literally have to be identical simultaneously. It is an all-or-nothing game. Hybrid states are strictly forbidden. The subunits either click over from the tense T state to the relaxed R state altogether, or they don't change at all. The ligand is just shifting a pre-existing macro equilibrium. And this brilliantly illustrates the alternative, the sequential or KNF model. Instead of that rigid all-or-nothing shift, this model relies on induced fit. Basically, a ligand causes a localized change in just one subunit. Because of this, hybrid states actually do exist. You can totally have a mix of T-state and R-state subunits hanging out in the same protein. But the absolute most important takeaway for your exams is this model's ability to explain negative cooperativity, which is where binding a ligand actually decreases the affinity of the adjacent empty sites.
To wrap up our explainer today, I want to leave you with this. We know from Leventhal's paradox that a protein cannot possibly just randomly sample every single conformation to find its folded state. I mean, doing that would take longer than the age of the universe. And if it falls into a kinetic trap, it could misfold into these toxic amyloid fibrils like the ones we see in Alzheimer's disease. So how does it find its shape so flawlessly? The answer lies in molecular chaperones. These are specialized biological machines that shield vulnerable proteins from the chaotic cellular environment. It proves that while the code is definitely in the sequence, sometimes life just needs a little bit of help to find its perfect form. Well, thanks so much for joining me in this explainer. I really hope exploring this review guide together has helped clear up these concepts, and I wish you the absolute best in your continued studies. See you next time!